Hello guys, I wanted to go ahead and just give you a quick review on torque, and I also wanted to go over some of these torque problems that you've been asking me to do. So first of all, torque is the ability of a force to cause rotation, okay? Now, in order for something to rotate, that's going to depend on the magnitude of the force, the distance the force is applied from some pivot point, and the angle at which it is applied at. There are two ways to find torque that we've talked about in class. We can either look at the perpendicular component of the force times the radius, or another way to find torque, we can look at the force multiplied by the moment arm. Okay, now the moment arm is the perpendicular distance from your pivot to your line of action, and your line of action would be along the force. So if I wanted to find the moment arm for this force, I would just extend my line of action and make a 90-degree angle with this radius here. So this distance would be our perpendicular in that case. I want to start by looking at number 4 here. The others were pretty simple. I'll give you the solutions, but I'm not going to do the videos for those. The tune-up specifications of a car call for spark plugs to be tightened to a torque of 38 Newton meters. I'm going to go ahead and write that down here because it's some information that I know. You plan to tighten the plugs by pulling on the end of a 25 centimeter long wrench. Because of the cramped space, you'll need to pull at an angle of 120 degrees with respect to the wrench shaft. With what force must you pull? Okay, so first of all, I'm going to draw my wrench here. And it doesn't matter where your 120 degrees lies. You can have it here or here. Some people argue, and it's not really an argument, it's a very valid statement. If you're tightening something, then you're going to pull in a clockwise motion. So that 120 degrees should be represented here, in which technically this torque should be negative. So in the problem, it's talking about a magnitude of the torque. We don't really need to worry as much about where that force is applied, but we know we're going to apply some force at 120 degrees to this axis for my wrench. Now the wrench has a length of 25 centimeters, that's 0.25 meters. So now we can go ahead and look at our equation. I need to find my perpendicular force. Now my perpendicular force is going to be this component. It's the part of my force which makes a 90-degree angle, and that doesn't really look like 90 degrees, but a 90-degree angle with your radial axis here. So this is F perpendicular. Now if I look at this, that just made a 90-degree angle. So I know that the angle between F perpendicular and F should be 120 degrees minus 90 degrees, which is 30 degrees. Okay. Now, my job is to find the torque, or find what that force is. So, my torque is going to be equal to F perpendicular times my radius. So I know my torque is 38 Newton meters. So I can solve for F perpendicular. So F perpendicular is 152 newtons. Now some of you wanted to stop here. You said, well, I found a force. You only found this component. The problem said, what is the force? It didn't ask you what part of the force is going to cause the torque. It said, well, what force are you going to be applying? So you have to actually use this right triangle here and find the length of our hypotenuse, F. Okay, so because this is my side adjacent, I'm going to say the cosine of 30 degrees is equal to my F perpendicular over my hypotenuse. So we can see that F, the actual force, is going to equal 152 newtons, or my perpendicular force, divided by the cosine of 30. And that should give you 175 or 176 newtons. Okay, so here we're dealing with a door. It gives the dimensions of the door, which I don't know right now if those are even important to the problem. It gives the mass of the door. We know it's going to pivot about some hinge, so I'm going to draw the door. This is a top view of the door here. A door closer is attached to the door and the top of the door frame. So I know there's going to be a torque provided from this door stopper or door closer. When the door is open and at rest, now because it's at rest I know it's not rotating, therefore my net torque is going to equal 0. That means the sum of all of the torques on this door will be equal to 0. It says the door closer exerts a torque of 5.2 Newton meters. So I know the torque caused here is going to be 5.2 Newton meters. Now that's just the magnitude. Based on my picture, it looks like that torque should actually be negative. Now this says what is the least force that you need to apply to hold it open. So I know that if I want to hold this door open, I'm going to have to apply a torque equal in magnitude to this. So I need to find the force, and I know that if I'm going to apply the least amount of force, I need to push perpendicular to the door. Okay, I don't need to push on the door at any angle. If I know my torque and I'm looking for my force, I'm going to also need the radius. So do I know this distance if I'm standing at the end of the door? Well, it says the door is 0.91 meters wide, so that's this distance right there. Now I'm just going to use this information, 5.2 equals my force times my radius, and I'm going to solve for the force. This is the least amount of force that I will need to stand here. So 5.2 divided by 0.91, you get 5.7 newtons. And that's a relatively small force, so I'm okay with that answer. Number 6. It says we have F2 acts half as far from the pivot as F1. What's the magnitude? What magnitude of F2 causes the net torque on the rod to be 0? So let's go ahead and just look at our torques. F1 is 20 newtons, but we know it's actually, we're going to have a perpendicular component here. And it is applied at a radius we will call R. F2 is applied at a radius then of R over 2. Okay, that's given in the problem. This force here would cause a counterclockwise torque, and this force would cause a clockwise torque. So in order for the net torque to be 0, that basically means the sum of all our torques must be 0. We would have a positive torque here. I want to say the torque caused by F1 minus the torque caused by F2 must equal 0. So what is the torque caused by F1? Well, first of all, I have to find my perpendicular component. And that perpendicular component is going to be 20 times the sine of 45 degrees. Now, I've already taken care of the fact that this is negative here with subtraction, so when I look for the torque of F2, I don't need to have a double negative. I only need to use the negative once. So F2, the torque for F2 would be, it's already perpendicular, so there's no need to do anything there. So F2 times R over 2. Oh, I forgot to put my radius here. So this is force perpendicular times our radius minus F2 times its distance from the pivot has to equal 0. I'm just going to rearrange this a little bit. I'm going to go ahead and calculate 20 times the sine of 45. So if we look at this, there's an R in each term, so the fact that we don't know that distance, that's okay because it cancels. So it looks like F2, then if we multiply 2 on both sides, is going to be about 28 or 28.2 newtons. Okay, here we have Tom and Jerry. Basically for this problem we just need to find the perpendicular components of Jerry's force and the perpendicular components of Tom's force. and they're both going to have the same radius. If it's a 3-meter diameter, then the radius for both of them is going to be 1.5 meters. If Tom pushes with a force of 50 newtons and Jerry pushes with a force of 35 newtons, what is the net torque on the merry-go-round? So here I just need to add up these torques to get my net torque. So A, first of all, our perpendicular force for Jerry. This force right here of 35 newtons becomes our hypotenuse. And I need to understand how this 80 degrees comes into play. Well, if this is 80 degrees, then this angle right here must be 10 degrees. That's going to be a 10-degree angle, and that's because if I extend that radial line, these are vertical angles, 80, and so that would make this one 80. And because 80 and this perpendicular force make a 90-degree angle together, that's why that has to be 10 degrees. So basically, if I zoom in on this triangle, I have this. I have 35 newtons. I'm looking for my perpendicular force. That's 10 degrees. And there is my right angle. Looking at this, I need to use cosine. So I'm going to have the torque for Jerry equals negative, because it's going to cause him to move clockwise. So negative 35 times the cosine of 10 degrees. There's our perpendicular force times our radius, which is going to be 1.5. And the torque for Tom, if this is 60 degrees, that makes this 60 degrees. So that means that this small angle here must be 30. Now if I zoom in on that triangle, looks like Tom pushes with a force of 50 newtons. This is going to be 30 degrees. And I'm looking for this perpendicular force, so I'm going to use cosine again. And Tom is going to cause a positive torque because it's counterclockwise. So I'm going to say 50 newtons times the cosine of 30 degrees times 1.5 will give me Tom's torque. And then I will just add those together to get the net torque for part A. 13.2. Okay, to do B, it says that Jerry reverses his direction by 180 degrees, so that just means that we're going to have another positive torque here. The y component is going to be exactly the same as the y component over here. So Jerry's y component was 35. The only thing that's changed is instead of a negative torque, it's going to be a positive torque. Plus 50 cosine of 30 times 1.5. That will give you your new net torque with both of those forces being applied in the same direction. And when you do that, you get 117 Newton meters. Alright, 8, 9, and 10, I'll deal with the same 8 Newton force and 10 Newton force. It's just asking you to find different torques, or the 8 Newton force changes its location. So the net torque on the bar shown is going to be equal to this force of 10 newtons times the distance from the pivot, which is 75 centimeters. This 8 newtons has no perpendicular component, so it has 0 torque there. And this is a counterclockwise torque, so it's positive. So the net torque here is just 7.5 Newton meters. Okay, now number 9. The only thing that's changed is this is going to be a positive torque, and this 8 Newton force will cause a negative torque. So to find my net torque, I'm going to take the force. Now there's no trick here because there are no angles. Both of these forces are already at 90-degree angles. So I'm going to take 10 newtons times 0.75 minus this force here is going to cause a rotation in that direction. That is clockwise, so it's going to be negative. That's what we subtract. Now I don't want to do minus and negative. I don't want to have a double negative there. I only need to take care of it once. So 10 times 0.75 minus 8 times 0.25 is going to equal my net force, and when I do that, I'm going to get 5.5 Newton meters, and that is a positive, so it's still going to go this way, and that makes sense because this is a larger force and a larger radius. Number 10 is very similar. However, now we have the 10 Newton and 8 Newtons both pulled at angles. So I need to find F perpendicular for the 10 Newtons, and I'm going to have to find F perpendicular for the 8 Newtons as well in order to use my torque equation. So this is my side opposite, and I have my hypotenuse here. That means I'm going to use sine. This perpendicular force is going to equal 10 times the sine of 30. And the perpendicular force over here for my 8 Newton force is going to be 8. We're going to use sine again because it's opposite of my 40 degrees, and 8 is my hypotenuse, so that's going to be 8 times the sine of 40. Now if I put that in an equation to find the net force, I know this is going to be 5, sine of 30 is a half, but if I didn't, I would just write it out. I like to always write out my equations before I go to my calculator. Sometimes it gets a little tedious, but it's going to be this force, this perpendicular force times the radius, minus this perpendicular force times its radius from our pivot. Now again, I've already taken care of the negative. I don't need to say times a negative 0.25. And that equals 2.5 Newton meters. A drum of chemical waste has a lid with a radius of 35 centimeters. To open the thing, a torque of 367 Newton meters is required. What force must you work on the thing? I'm going to go ahead and write what I know. R is 0.35. My torque is 367. So I can pretty much just use this simple equation to find my force. And we're going to assume that it's wanting the least amount of force, which means it's talking about my perpendicular force. 367 equals F times 0.35. So F is going to equal 1,048.6 newtons. I, of course, would just round that to 50. Alright, a pair of adult nitwits sit balanced on a teeter-totter. Balanced means the net torque is going to be 0. One of them, whose mass is 42 or 45.2 kilograms, is 1.3 meters away from the pivot. The other is 2.15 meters from the pivot. So what is the mass of the second person? The first one, sitting 1.3 meters away, has a mass of 45.2 kilograms. I can very easily find his weight by multiplying that by 9.8. Okay, the other person has a mass, m. I don't know what it is, so I'm just going to call it m. Its force of gravity would be multiplied by 9.8 as well. Now, because this is balanced and they're on opposite sides of our point of rotation, this is going to have a counterclockwise torque. This is going to have a clockwise torque. These just needs to be equal to each other. So I'm going to say 45.2 times 9.8 times the radius must be balanced with this force, m, times 9.8 times the radius. Now if you look, this 9.8 just cancels. So if I do 45.2 times 1.3 and divide that by 2.15 to solve for the mass, I'm going to get 27.3 kilograms for the second person. Alright, that is all for these problems.